In this video, we're going to look at the properties of integrals and how we can use integrals to find average values of functions. First, we need to recall back on even and odd functions and what makes a function an even function, what makes a function an odd function. Now, keep in mind, not all functions can be classified as either even or odd, but some that can be classified as either even or odd can give us some nice symmetries that we can evaluate integrals a little more simply. So pictured here is an even function. Now, why is it even? Well, the analytical definition is that f of negative x is equal to f of x. The graphical definition of that is that we have symmetry about the y-axis. So if we fold the graph along the y-axis, we'll see that the curve lines up. Where we go up and to the right, we also go up and to the left coming from the origin. So this graph here depicts an even function. And if we notice, looking at the area under the curve, from some value negative a to 0 at the origin, and from that same value at 0 out to positive a, we notice that these two regions have the same area. So we can use that when we have to evaluate an integral from negative a to positive a of an even function. So if this function is even, then we can say that, well, this is just 2 times the integral from 0 to a of that same function. Now, sometimes this symmetry helps. It's a little bit of a shortcut. Sometimes it's insignificant and we need to pay it no attention at all. But it's just something that we can have to hold on to use and possibly simplify a situation. However, odd functions act in a similar way, but even a little nicer in that when we look at an odd function, now first off, what is an odd function? Well, the analytical definition is that we have f of negative x is equal to negative f of x, or on a graph, we're symmetrical about the origin. So if we go up and to the left, then we have to go down and to the right past the origin. And so with odd functions, we have the same area to the left and to the right from negative a to the origin, from the origin to a, but the difference is one region's above, one region's below. So if they're the same area, one above, one below, then that integral is going to cancel out to 0. So this is nice in that if we have some odd function that is a nasty function that we can't use antiderivatives to evaluate, but we're going from negative a to positive a, then we can sometimes simplify it to just say, well, we know that this is going to be 0. Now, if we were to ask, well, what's 0 to a? Well, we don't necessarily know. We would then have to evaluate the integral by finding the antiderivative or using some geometry or something along those lines. So this theorem states that if we have some positive value a and we go from negative a to a, quite simply, if the function is even, we can simplify the integral to 2 times 0 to a, and if it's odd, then we know that integral simplifies to 0. Let's use this in an example here. If we have the function x to the fourth minus 3x cubed dx, and we want to integrate from negative 2 to 2, first off, we have to identify that can we even use these symmetries, and we can because we have symmetry in the bounds. We go from negative 2 to 2. And so we ask ourselves, what type of function is this? Is this an even function or an odd function? Well, looking at it, this is a polynomial. The highest degree is 4, so that makes us think that it's an even function. However, we got to make sure this is only going to be an even function if it goes through the origin or it's shifted up with the type of symmetry such that it is still symmetrical about the y-axis. So sometimes it's helpful to test, is this an even function or not? Let's pick a value. Let's put in 1. If we put in 1 in here for both x's there, we get 1 to the fourth minus 3 times 1 cubed. That gives us a negative 2. Well, what if we put in a negative 1? If we put in a negative 1 here, that becomes positive 1, and then when we put in a negative 1 here, we get negative 1 cubed, which is negative 1 times a negative 3 is a positive 3. And so when we put that in, we get 4. So notice, this is not an even function, nor is it an odd function. So we cannot use those symmetries. So in this one, we have to use the fundamental theorem, find our antiderivative, evaluate it to and subtract our antiderivative evaluated at -2. So if we were to work this out, we notice we can't use any symmetries. We have to go about it without using the symmetries, and we get x to the 5th divided by 5 minus 3/4 x to the 4th plus c, but we don't really need the plus c because we are going to evaluate from -2 to 2. If we evaluate this, we then get 64/5. Now we can look at this same function, but in a slightly different way so that we can use those symmetries to help us out. So we know that with integrals, if we're integrating this function, which is really a combination of two functions, we can split that up to say that it's the integral from -2 to 2 of x to the 4th minus the integral from -2 to 2 of 3x cubed. And both of these are with respect to x. So using this, then we look at, well, x to the 4th, that is an even function. That's the same thing as the integral from 0 to 2, and we multiply by 2 of x to the 4th dx minus, well, 3x cubed. X cubed is an odd function, so we know that this is going to go away to 0. And so right away that simplifies this down to, well, we don't need that second portion of the function because it's an odd function, and we get rid of it. And this just becomes the antiderivative of x to the 4th is x to the 5th over 5 evaluated from 0 to 2, and then we're going to multiply by 2 in the end because of this 2, because of our symmetry. And now it's a lot easier. Plugging in 0, we don't have to do any addition or subtraction of fractions to find a common denominator. We can just evaluate 2, and 2 to the 5th is 32 times 2 is 64. And this gives us the end result of 64/5 much more quickly. So let's use that same rationale and let's look at the second one here. Even though this function cosine x minus 4 sine cubed of x is not necessarily even or odd, we can split it up to say that, well, it is the integral from -pi/2 to pi/2 of cosine of x minus the integral from -pi/2 to pi/2 of 4 sine cubed of x. All right, and then using this, we can ask ourselves, do we have any even or odd functions? Well, cosine is an even function, so that simplifies to 2 times the integral from 0 to pi/2 of cosine of x dx. And sine is an odd function, but it's an odd function that's being cubed. And the question is, does that remain odd? And so let's think about this in a polynomial sense. If we had, say, x is an odd function, and if we cube that, does that still remain an odd function, or does it become an even function? Well, x being cubed is x cubed, which is still odd. So an odd raised to an odd power remains odd, and so this goes to 0. Now, the converse to that would be that if we have an odd function raised to an even power, that becomes an even function. But that's not what we have here. So this goes off to 0, so we don't even have to worry about that sine cubed x, which is a good thing because we have no idea how to get the antiderivative of that at this point. However, we can get the antiderivative of cosine of x, and that will be sine of x, and we want to evaluate that from 0 to pi/2, and sine of pi/2 is equal to 1, and sine of 0 is equal to 0, so this integral simplifies to 2. Finally, we're going to look at how the integrals allow us to find the average value of a function. And so the average value of a function is going to be defined as f bar, and we call this f bar here because there is a bar over top of f, which that bar means the average value. So the average value of some function f on an interval from a to b is equal to 1 divided by the interval width here, b minus a, times the integral from a to b of f of x dx. So let's think about conceptually what this means. Well, What is this piece here? This integral, that is an accumulator. It's accumulating all the values of f between a and b. And so it's adding up all those values, all the area underneath the curve. And then we're dividing by the interval width, so that's giving us a per x value. So it's giving us the sum of all the x, or the sum of all the rate of change of x per x. And so that gives us an average value. So that gives us an average y per x. So we can use this to calculate the average value of any given function. Let's look at an example here. We have some function f of x is equal to 60x cubed minus 650x squared plus 1200x plus 4500, where f is the feet above sea level and x represents the horizontal distance along a trail in miles. And so on the interval from 0 to 5, what is the average elevation of this trail? Well, that average f is going to equal 1 over the b minus a times the integral from a to b of f of x dx. So to find the average value here, we just have to have 1 over our interval width, which is 5 minus 0, so that's 1/5, the integral from 0 to 5 of this function, 60x cubed minus 650x squared plus 1200x plus 4500. And we want to do all that with respect to x. And in order to do this, we need to do our antiderivative. So you get 60x to the fourth over 4. So that's going to give us 15x to the fourth. And then we want to subtract 650 over 3, which we'll just write 650 thirds x cubed plus 600 x squared plus 4500x. And we evaluate that from 0 to 5. Nice thing is, plug in 0 and everything goes away. Plug in 5, you're going to get a fraction, but you'll get 59375 over 3. So 59,375 over 3, or just under 20,000, approximately 19,791 feet above sea level. And that is our average value of our elevation above sea level along that trail from 0. Wait a minute, we forgot to use this 1/5 here. So we actually want 1/5 of this whole quantity here and 1/5 of this quantity here. So that would give us approximately 4,000, just under 4,000 feet, because it's about 20,000. Fifth of that would be 4,000. And so if we look at the graph, we can see that the average value, if we graph that just under 4,000, and this is the elevation of the graph here, we see that that is the average value of the trail from 0 to 5 miles. Now let's think back to the mean value theorem. And we had the mean value theorem back with derivatives, but this can still be applied to integrals here. And so if we have a function f and it's continuous on the interval a to b, there exists a point c such that the average value is equal to that the function is equal to the average value at that point c. So this is kind of going backwards. If we remember, the secant slope is equal to the tangent slope. That was the mean value theorem with the derivatives. But the mean value theorem for integral states that if this is a continuous function, there has to be somewhere on the function that we are equal to the average value. And looking back at this graph, yeah, that point existed right here, where our average value is equal to some value in our function, and this is somewhere around 3, and we could, set that equal to the average value to solve, but we just know that it has to exist somewhere. Using this, we could find the points on the interval from 0 to 1 for which the function f of x equals 2x times quantity 1 minus x is equal to the average value. Well, the average value is equal to 1 over 1 minus 0 times the integral from 0 to 1 of this function 2x times the quantity 1 minus x dx. And to do this, I would distribute this to say that's really 2x minus 2x squared. And so we're going to evaluate this, and that will be x squared minus 2/3 x cubed, evaluated from 0 to 1. And when we do that, we get 1 minus 2/3, and so that's equal to 1/3. So the question is, when is f of x equal to 1/3? So we can set this equal to 1/3 and solve, or we can look at it graphically to see that we have 2 points in which this occurs, because we have 2 points where our average value is equal to a value on the curve of the function.